Imagine a new computer system that could create virtually unbreakable encryption, supercharge the development of artificial intelligence, remodel traffic systems, and radically expedite the development of drug treatments for everything from cancer to COVID-19.
Today we see Chicago and its esteemed university as the incubator for technology that will change the world.
This technology, quantum computing and the quantum internet. Quantum science is one of the most important technological frontiers of the century, and the Department of Energy is partnering with the University of Chicago, Argonne National Laboratory, and Fermi National Laboratory, and others to develop it, all within the decade.
It's not a stretch to say that when fully built, the quantum internet will bring incredible, unexpected benefits, much as today's internet's already done.
This is U.S. Energy Secretary Dan Brouillette speaking earlier this summer at a University of Chicago event. He was there to announce a strategy that will bring the country to the forefront of the global race to help create a quantum internet. To understand what that means, we turn to David Awschalom. David's a professor in quantum science and engineering at the University of Chicago, and he's one of the leading experts in the field. So I asked him, how will the quantum internet change the world?
Over 50 years ago, when today's internet was created, very few people could have envisioned how we actually use it today. So now you're asking a great question. How will we interact with a fundamentally new technology down the road? And like the internet before us, this absolutely will impact our lives.
From the University of Chicago, this is Big Brains, a podcast about the pioneering research and pivotal breakthroughs that are reshaping our world. On this episode, building a quantum internet. I'm your host, Paul Rand. It can be hard to imagine life before the internet.
Tonight, the information superhighway and one of its main thoroughfares, an online network called Internet.
What is Internet anyway?
Massive computer network. The one that's becoming really big now.
What do you mean? That's big. How does one? What do you write to it like mail?
Imagine, if you will, sitting down to your morning coffee, turning on your home computer to read the day's newspaper. Well, it's not as far-fetched as it may seem.
But what if there were a new internet? One that would make our current one look like a tool from the Stone Age. Well, that's what the quantum internet could be. Unimaginably powerful computers communicating over unimaginably fast networks to tackle the world's most unfathomable problems. So, how will it do that? What will make the quantum internet quantum?
Right now, our internet works because our unit of information consists of zeros or ones. For quantum technologies and quantum computing, the quantum unit of information, or the qubit, isn't just 0 or 1. It's an infinite combinations of zeros and one. The data represents itself in a fundamentally different way. It's a little bit like going between black and white in color.
Toto, I have a feeling we're not in Kansas anymore.
The other magic ingredient about a quantum internet is entanglement.
Entanglement. You may have heard of the term before. It's a complicated phenomena that means that particles can share information with each other, even if they're in different locations.
We can create information and share it between two objects, or two quantum bits if you like, and put those quantum bits over arbitrary distances, whether it's Chicago and San Francisco, or Chicago and London, it doesn't matter. And if I look at one of them, it impacts the other. There's a connection between the two without a physical connection, and this is called entanglement. You can share information among many objects, and the act of looking at one impacts the others.
The quantum effect of entanglement is something that Albert Einstein famously called spooky action at a distance. That, plus the strange fact that simply observing a quantum particle changes it. It's responsible for one of the most exciting parts of the quantum internet, that it has the potential to be virtually unhackable. If a hacker tried to intercept a quantum network, the act of just looking at the particles causes both to collapse. If researchers use entangled particles to send information between two locations, and a hacker tried to intercept that information, the message would be instantly altered.
For example, you could imagine an internet which would enable us to have secure elections, where people could participate in government processes, absolutely securing their information, knowing that it could never be eavesdropped upon or tampered with in any way.
That level of security is also very interesting to the financial sector. David, when you had an event here not long ago, you had some of the largest financial players in the world that were here looking and interested in quantum and how it would apply to the financial sector. Where do you think that area, the sector's biggest interests, are coming from?
The financial sector is looking at quantum technologies and trying to understand how their business challenges can benefit from them. Because one of the challenges in the financial sector is when someone performs a transaction, they want to be sure that nobody has extracted the information along the way, copied it, put it back, and then you receive it. And how do you know that you haven't received information that somebody has copied or tampered with? So they would love a technology where that will be virtually impossible. There's no way to extract the information without changing it. It's ultra secure. It's interesting to look at the financial sectors around the United States and see that they're also growing quantum groups. JP Morgan Chase has an extraordinary group of quantum scientists they've hired. So does Goldman Sachs. Places that a few years ago you might not have thought would be building quantum technology programs.
The initial uses of the quantum internet in computing will most likely be companies and institutions. Awschalom says that eventually individuals might use it too. And the possible scope of its applications at either level seem almost endless.
I think the way that people will end up interacting with the quantum internet will be driven by the applications and the needs. Quantum technologies will enable things like blind computing, where the owner of the technology has no way of knowing how you've used it, what you're searching with, what you're seeking to do. And you can also imagine a quantum internet building quantum supercomputers, linking quantum machines together to build larger systems to attack problems well beyond things we could imagine today, like drug designs, searching for vaccines, traffic control, energy distribution, scheduling problems. One interesting application that people are thinking about now, which will impact us, is taking magnetic resonance imaging down to the level of a single molecule. Imagine today if a hospital that does MRI scans, typically using 10 to the 20th molecules, could do MRI on one, that we could understand the structure and the functional relationship of every protein inside us. And today we can only do that with a few % of our proteins. It would revolutionize medicine. It would change the way that all of us deal with healthcare.
David, if I can, let me change gears just a little bit on one of the things. As a country and globally, we're facing a whole host of seemingly intractable problems. Whether it's COVID situation we're dealing with, whether it's the climate crisis that we're dealing with, and those things related to it, as you think about it, and I know that there's hope in many camps that possibly we can quote unquote science our way out of some of these things. Does that get any closer to reality as some of these new ideas in quantum start coming into place? That the ability to truly begin looking for some answers to some of the most perplexing things facing our world can actually be worked on?
I'm very optimistic that will happen because many of these challenges that you've just alluded to are challenging because they're very complex. Trying to identify a vaccine, for example, is very hard with a complicated virus that changes shape, reacts to its environment in different ways. How do you model these? How do you even begin to design a pharmaceutical? Could you design a system where you could test all different types of configurations, minimizing real-world testing? Having quantum technologies to attack these problems will certainly help fuel the discovery of pharmaceuticals. I think problems that we're facing about how to deal with clean energy and energy distribution efficiently, minimizing waste, how we'll deal with water purity with sensors around the globe to monitor and control our ecosystem. I think these are very complicated problems, even how you efficiently deliver packages, how you assemble aircraft. A 777 has over 3 million parts, for example, in a Boeing aircraft. How do you assemble them in the right order? How do you make that process much more efficient? You could use trial and error, or you could use an optimization algorithm in a quantum machine and solve it and know exactly the right order to do the assembly. I think we'll see lots of impacts on society as we learn more and more about the potential of this technology and get informed as to what are the most challenging problems with our partners. Where do they need help? And how can this quantum technology be used to assist?
It's clear that quantum technology holds a great deal of promise. But what's holding it back? and what will need to happen over the next 10 years for the Department of Energy and the university to realize the goal of creating a quantum internet. That's coming up after the break. Coronavirus is changing life as we know it on a daily basis. But how will the pandemic permanently reshape our lives in the future? What will our world look like 5 years from now? COVID 2025, Our World in the Next 5 Years, is a new video series featuring leading scholars at the University of Chicago. They'll discuss how coronavirus will change healthcare, international relations, education, and many other aspects of our lives. The series, from the same team that brings you this podcast, can be found on YouTube with new episodes released regularly. The quantum internet, as we said in the very beginning, has the power to change our world. But how do we get there from where we are today?
So to create a quantum internet, we have to build the quantum technologies like quantum computers and quantum sensors, and then develop a technology which will capture this information from the quantum machines and allow us to keep it in a type of ecosystem, keep the quantum mechanical nature of this information consistent and untouchable as it moves from one technology base to another. And that's a challenge. That's something we can't do with today's internet. Because at the end of the day, nature at its very smallest scale doesn't behave according to the laws of zeros and ones. It's not binary. It's more complicated. And nature moves information around quantum mechanically. And this quantum technology that we build and quantum connectivity also has to work differently and transfer information without touching it, keeping the quantum nature intact.
One of the biggest challenges in terms of keeping the quantum connection intact includes a key piece of hardware. And David Awschalom says that it's crucial to make sure that particles remain entangled over long distances.
We need to build a technology called a quantum repeater. One of the reasons that our internet works so well today is that we send light signals through optical fibers going all over the country. The reality is that when you send pulses of light through optical fibers, after 20 or 50 kilometers, the signal starts to drop in amplitude. Because in the real world, when you're sending light through glass, there are impurities in the glass, and the light scatters and becomes smaller and smaller as it winds its way down to the destination. And the critical piece of technology that lets me send the signal from Chicago to San Francisco is that we have small technologies every 20 or 50 kilometers called repeaters. They take this small signal, they amplify it, and they send it out again. And that lets us transmit all over the world. Now let's think about a quantum internet. We take a quantum signal and we send it down an optical fiber, where the quantum properties are encoded, say in the polarization of a pulse of light. We need an object or a technology that will read this signal, amplify it, and repeat it. But the laws of quantum physics have a fundamental problem with that, which is the act of observing something changes it. It's called the no-cloning theorem. You can't simply repeat a quantum signal, so you need to build a technology that can take this quantum property, move it somewhere else, read it in a different way, and send it out again.
Creating this type of hardware will require a new generation of quantum engineers. So far, there are about 150 quantum scientists in the greater Chicago area. That makes Illinois a leading center of this technology, both nationally and globally. But to execute the vision of a quantum internet within a decade, we'll need thousands of scientists.
When we talk to our industrial partners, both in the United States and around the world, one of their most pressing concerns is how will they have a sufficient workforce to meet the demands of the technology. There are two challenges. One is the fact that we're entering a time where there'll be a large number of retiring electrical engineers in the United States. The second is these companies will have to replace these conventional engineers with quantum engineers, people whose training covers quantum physics, material science, electrical engineering, materials research, with a new type of training that integrates all of these together to think about how we can use the quantum properties of nature to build targeted technologies. So the training is a little different. It's not the traditional academic discipline. It's more problem-based. It's mixing computer science with quantum physics. with engineering, with materials development, as I was just saying, and that does require a different educational platform.
And is this a transition that if you're in an existing field, that you can transition over with a relative amount of ease, or is this really a complete overhaul?
I think it's a combination. I think there are many fields where this transition can be made well. So we can imagine training programs that take today's engineers and allows them to slightly pivot with additional information to use their existing training for quantum technologies. But we also need to think about, from a very early age on, making people comfortable developing intuition about quantum science, something that few of us have. It's a very different way of thinking, and you need to be comfortable with this very non-intuitive way of thinking about information in general to devise new technologies.
Retraining will be a big part of creating this new workforce. At the University of Chicago, a first-of-its-kind program starting in a few weeks will enable classically trained scientists and engineers to transition to careers in quantum science. Now, the Department of Energy will empower 17 national laboratories to serve as the backbone of the coming quantum internet. And recently, the DOE launched 5 new quantum science research centers led by the national labs.
The Department of Energy centers, which were just announced, allow us to build consortia of leaders from around the United States to attack major challenges for quantum information science. The one here in Chicago is quite extraordinary.
It's a collaborative center called QNext,
focused at Argonne National Laboratory. That is a consortium of 10 companies, 10 universities, and 3 national laboratories, focusing on quantum connections to create and distribute quantum states of matter, quantum sensors to push the limits of quantum sensing, but also to establish a quantum foundry, 2 foundries, in fact, one at Argonne National Laboratory and one at SLAC in California, focusing on building the materials that will serve as the basis for these technologies. It's the first of its kind in the United States.
And so right now, where are those materials coming from?
Right now, materials tend to come from different research groups around the country. What many of us feel is important is to standardize the process, build a foundry where researchers around the country will have access to well-characterized, pristine materials that can be used for their specific application. Their tests and quantification of these materials will be fed back into a national database for companies, university researchers, and national lab researchers to analyze, study, improve, and distribute.
Even before the Department of Energy Center, Chicago was already a leading hub for quantum research. Earlier this year, scientists from the Argonne National Laboratory and the University of Chicago entangled photons across a 52-mile quantum loop. It goes from Argonne and Lamont, Illinois, around and through the suburbs of Chicago, using an existing underground network of optical fiber built decades ago for conventional telecommunications. Awschalom spearheaded the project, which is now among the longest land-based quantum networks in the country. It's able to teleport information almost instantly.
This is an extraordinary moment for Chicago and the state of Illinois, and that's been echoed by the remarkable support from the governor's office to devote enormous support to the construction of new facilities in Chicago to build laboratories for collaboration between students, our partners, our industrial collaborators to drive this research. It means Chicago can be a center for quantum information science and technology in the country, both through its leading academic programs, the state-of-the-art research at the national labs, these 2 DOE centers, and I should also say an exciting National Science Foundation Center established at the University of Illinois, Urbana-Champaign, to drive the workforce development and related technologies that will tie into this entire ecosystem. So with the appearance of national centers by different federal agencies, the national labs, major universities such as the University of Chicago, the University of Illinois, and Northwestern universities, we have an extraordinary opportunity here to become national leaders in this field.
And in your mind, David, what does a national leader or a global leader look like? What are the important investments that need to be made in growth right now?
It means that this area can drive discoveries in material science, new applications in partnership with companies, driving international collaborations, Paul, as you mentioned earlier, how we transfer some of the results to leaders around the world to go beyond the Chicago area, beyond the nation, and across the globe to impact standards, applications, developments of new technologies, development of new scientific efforts. It means we can attract some of the best scientists and students from around the world to engage in this effort, to think about how we can harness the very best ideas to ask the most challenging questions that emerge in science and technology. Because in the end of the day, we want the brightest minds, the most exciting ideas, the most impactful industrial partners that can help translate these scientific ideas into technologies here in Chicago, and to use this as a spring, if you like, where our students can be deployed everywhere and impact the world in this area.
David, you mentioned a little bit ago something about the Chicago Quantum Exchange. Can you just give us a little background on what that is and how it began and maybe any other aspects of it?
The Chicago Quantum Exchange began in 2017 when we began to think in the Chicago area, with the benefit of two national laboratories and major universities such as the University of Illinois and the University of Chicago, how could we build an enterprise that could identify large opportunities and work together to aggressively compete for them? And that was the birth of the Chicago Quantum Exchange. Also, knowing that we can't do this alone. We need to do this in partnership with industry. And we need the mechanism to drive and attract the best companies to work with us in this field. So once the national labs and the academic partners got together, we launched an endeavor which now has over a dozen companies very heavily engaged in the quantum exchange, exchanging researchers, ideas, student internships, new grant proposals, attracting new research opportunities for students. As a measure of their enthusiasm for this Department of Energy Center, our industrial partners have committed over $60 million of their own resources to help drive the science and technology effort. It's an extraordinary engine now that will help drive quantum technologies here in Chicago.
Let's look at the Chicago area 5 years out. Let's look at progress in the field 5 years out. What kind of things are you looking for? What kind of progress do you expect and hope to be making collectively?
Well, we expect to establish test beds in the Chicago area, working prototypes where students and companies can work together and literally try out some of the ideas to optimize the technology and push applications.
As we were talking about corporate partners, and there are many things that are happening, but one that's really quite interesting and exciting is some of the work that Intel is doing in terms of the test spat out of Argonne. I wonder if you can give a little bit more context around that.
As part of the Argonne-led DOE Center, Intel will be commissioning the first semiconductor quantum computing testbed in the country, and that will be happening in a specially built laboratory at Argonne. The intent is to open up that quantum machine to users both within the center and ultimately around the country to run quantum computing algorithms, see what we can do with a chip-based quantum machine, and think about how we can scale that to larger quantum technologies. For example, Argonne National Lab has launched the Quantum Loop, a testbed for quantum communication, creating entangled states of matter, testing the security of quantum information transmission, and setting up a testbed that we'd like to extend here into the city, not just for the financial institutions to begin to test applications for quantum information transmission and security, but also for students at all levels to understand encryption and security, whether they're the Chicago Public Schools students, different high school students working in internships, undergraduates, students at two-year colleges, students from the universities around the area, all using these networks and prototypes to try out these ideas and learn and inform us. So I see us building these systems together, linking the national labs, Argonne and Fermi Lab, building local quantum internets in Chicago, using local companies to try out concepts and ideas on these internets, and building upon that. So I think we'll nucleate lots of new activities with these prototypes, and we're very optimistic that these will be launched in the next year or two alone.
So if we think back in the beginning of when Silicon Valley was created, do you think that we're in that similar phase of birth here in the Chicago area and Illinois, and we're going to start doing some of the things and experiencing some of those same growth and impact that the Silicon Valley has experienced for years?
I think with the leading companies, the leading students, the attraction of venture capital funds to the Chicago area to drive these initiatives, when we're successful at launching startup ventures around the Chicago area, I see absolutely no reason that Chicago can't be the next Silicon Valley for quantum information science and technology.
Big Brains is a production of the UChicago Podcast Network. If you like what you heard, please give us a review and a rating. The show is hosted by Paul M. Rand and produced by me, Matt Hodap, with assistance from Alyssa Eads. Thanks for listening.